Agentic AI has surged in popularity and has become an important tool to handle many complex, ever-changing tasks like writing blogs, running an analysis, automating repetitive workflows. One common challenge when working with agentic AI is dealing with new information when it is available. Agentic AI uses generative models like OpenAI GPT models as a base, but has the ability to think, plan, and act on its own. You can sync a generative model as a library. Every once in a while, it will purchase new books to add to its collections. And that's the same thing with generative models. You have to periodically update the model with new training data to make it more intelligent and generate more accurate, relevant responses. To overcome this challenge, that's where retrieval augmented generation comes in. Retrieval augmented generation, is called RAG, is a technique used in natural language processing and AI, where a model first retrieves relevant information from a data source and then use that information as context to generate a more relevant and accurate response. In this PydanticAI tutorial, we are going to learn how to create a RAG agent to retrieve information from a RAG database to generate more accurate and relevant responses. This is going to be a beginner-friendly tutorial, even if you have never used the PydanticAI framework before. PydanticAI is a Python agent framework designed to make it easier to build production-grade applications with generative AI. The framework provides a structured way to interact with LLMs, supports multiple AI models, and integrates seamlessly with Pydantic for type safety and validation. There are quite a few RAG databases out there today. Some of the popular ones like ChromaDB, Pinecone, Weaviate, and Milvus are all vector databases. Other relational databases like Postgres with PBG vector extension, MongoDB Atlas vector search, and Elasticsearch can also support RAG by integrating vector search capabilities into data storage solutions. When it comes to RAG database, LanceDB is probably my to-go knowledge database, and that's the RAG database we'll be using in this tutorial. LanceDB is an open-source vector database designed to work with agentic AI, specifically for efficient management and retrieval of embeddings on multimodal data. The database offers high performance and fast access for machine learning workloads and is highly scalable. Now, to integrate RAG with an AI agent, we must first need to understand some of the commonly used chunking strategies. Let's break them down one by one. There are 7 chunking strategies that I am aware of. The most popular and easiest chunking strategy is the fixed-length chunking, which is the RAG approach we will be using to integrate with PydanticAI today. With this chunking strategy, text is split into equal-sized chunks. Fixed-length chunking is commonly used in large-scale document indexing and embedding-based search, where speed is more important than precise chunk boundaries. I believe ChatGPT knowledge base is also using fixed-length chunking to store the knowledge files. When it comes to pros and cons, fixed-length chunking is extremely fast and easy to implement, which makes retrieval more predictable. The downside is, because it chunks the content evenly, it may cut off meaningful sentences and lose context between chunks. Next, we have the sentence-based chunking. With this approach, instead of chopping text at arbitrary points, this strategy keeps sentences intact, making sure each chunk is meaningful on its own. For example, imagine you're summarizing news articles. A fixed-length approach might break a sentence halfway through, making the summary incoherent. But with sentence-based chunking, each chunk is a complete sentence, so your AI can generate better, clear responses. The pros with sentence-based chunking is that it preserves the full context of a through, making retrieval much more natural and meaningful. The downside, however, is the chunk sizes can vary. Some sentences are short, some are long, so your data won't be evenly distributed, which can lead to inefficiencies in how embeddings are stored and retrieved. Now let's look at the next chunking strategy, recursive text splitting, which works in a top-down approach. It first splits text into large sections, like chapters or headings, then breaks those down into smaller paragraphs, and finally into individual sentences. Recursive text splitting is mostly used in legal documents, research papers, and technical manuals, where retrieving information in a structured format is important. The catch is, it's more complex to implement than other chunking strategies. It may not always be necessary unless you're dealing with large, structured documents. Moving on, overlapping sliding window chunking, which ensures that each chunk slightly overlaps with the next, helps maintain context between splits. For example, when you watch a TV series, at the start of each episode, the creator often gives a quick recap of the previous one to remind you of key points. This strategy works the same way, by carrying over part of the previous chunk into the next one, making sure no important details are lost. This strategy is widely used in chatbots, conversational AI, and long-form content retrieval, where maintaining context across chunks is critical. The drawback with this chunking strategy is it increases storage and processing costs because each chunk contains duplicate contents. Semantic chunking, which uses AI to determine the most logical points to split text, ensures that each chunk contains a complete, meaningful text. Unlike fixed length or sentence-based methods, this approach doesn't rely on arbitrary size limits or simple punctuation. Instead, it analyzes the meaning behind the text and intelligently groups related content together. The biggest advantage with semantic chunking is AI will be able to retrieve coherent and contextually rich content, leading to more accurate and relevant responses. And the downside is it's computationally expensive and requires using a generative model. Alright, 2 more chunking strategies to go. Metadata-based chunking, which chunks text based on existing structure, like headers, timestamps, or tags. This makes it perfect for structured data, but not the best fit for free-flowing or unstructured text. Metadata-based chunking is mostly used in enterprise document management, compliance tracking, and meeting transcript analysis, where predefined sections matter. And the last chunking strategy I'm going to share is graph-based chunking. This chunking strategy probably takes the most effort to implement, given the chunking approach is extremely useful for complex knowledge retrieval and can be used in just about any use case. Graph-based chunking is best suited for knowledge graphs, scientific research, and enterprise-level AI assistance where complex relationships need to be understood. Instead of breaking text by size or structure, the graph-based chunking analyzes the relationships between concepts and creates chunks based on meaning. And to summarize, if you are working with structured documents, go with metadata-based or semantic chunking strategies. If you are working with just text like a letter or novels, then go with sliding window or sentence-based chunking strategies. For large documents with defined sections or chapters, use recursive splitting. And for real-time applications, fixed length and overlapping window might be ideal. Graph-based chunking, which I forgot to put on the list, can be used with documents that require dealing with complex relationships, knowledge, or entities. Now that we have covered the most common chunking strategies, let's learn how to integrate RAG in PydanticAI. Launch your terminal and run the command to install PydanticAI LanceDB, TikToken, and tentative Python libraries. You will also need to install Python library to access generative models like OpenAI, Gemini, or Anthropic. When it comes to working with RAG, The first thing we need to do is to set up a knowledge database. To get started, open your code editor and create a Python file named LanceDB setup.py. For text embedding, I'll be using OpenAI's text embedding 3-small model to convert text into numerical vectors, which group text with similar meaning together. In the script, import the Python packages showing on the screen. I'll go through them once we get into the functions. Now let's create the helper functions to set up a LanceDB vector database. To convert knowledge text into a numerical format, set up an embedding function called OpenAI Func using LanceDB's getRegistry function with OpenAI as the provider, and text embedding 3-small as the embedding model. Next, set up a data model class with LanceModel to store document records. The document data model controls what data points will be stored in a LanceDB table. In this case, I'm only going to include ID, text, and vector in the table schema. In the document class, we can use the OpenAI Func function to simplify the field definition to make the embedding conversion a bit easier. To chunk content within the embedding model limit, create a function called chunkText with text, max tokens, and encoding name parameters. We will use this function to split a large text content into smaller pieces based on OpenAI embedding model token limits, which is 8,192. If we look at the function, we first obtain the proper tokenizer using the specified encoding name, then encode the entire text into a series of tokens. Next, step through these tokens in segments defined by the maximum token limit, decodes each segment back into text, and yields it. This way, you end up with smaller, manageable pieces that can be processed without exceeding model limits. The create LanceDB table and drop LanceDB table functions are used to create and delete a table in a LanceDB database. If we look at the create LanceDB table function, DB path is the file path where a database is stored. If the LanceDB database file hub path does not exist, the LanceDB connect function will create it automatically. Table name should be self-explanatory. The table where knowledge data will be stored. And overwrite indicates whether to replace an existing table or ignores if table already exists. Inside the function, connect to a LanceDB database, then create the knowledge table with the document schema to define the fields and table mode. Then use the create full text search index function to add text field as search index. If you want to add multiple fields, insert a list with the field names. And to drop a table in the drop LanceDB table function, call the drop table method with database path and table name as the arguments. When it comes to knowledge document type, I always make sure to convert everything into Markdown. To add knowledge files to a LanceDB table, create a function called add documents to table with 3 parameters: table, knowledge base directory, and max tokens. If we look at the function, we start out with an empty docs list and the knowledge base path where the knowledge files are located. Then iterate each Markdown file and use the chunkText function to chunk the content into reasonable size and add it to docs list. Once we have loaded all the knowledge content in a list, we then use LanceDB table add method to upload the knowledge data. When we define the knowledge storage table, we already instructed the data type for each field, so when the documents are uploaded, the document data model will automatically perform the vector conversion, which saves us a lot of hassles not needing to convert text into vector number first. To query relevant context from a knowledge database, create a function called retrieve similar docs with the 5 parameters: table, query, query type, limit, and re-ranker weight. query is the search string you pass to the table to retrieve relevant results. In LanceDB, there are 3 different query types: vector search, full text search, and hybrid search. Full text search will return text strings that match the query string. Vector search will search the approximate or exact nearest neighbors to a given query vector. And hybrid search will take both semantic and keyword-based search, using re-ranker weight to determine how much weight to give semantic versus keyword results, blending them for better results. Here, re-ranking is the process of reordering a list of items based on some criteria. This can be useful when the initial ranking of the search results is not satisfactory, or when the user has provided additional information that can be used to improve the ranking of the search results. In this case, I am using linear combination re-ranker, which re-ranks search results based on a linear combination of full text search and vector search scores. If we look at the search function here, basically, we are saying find the documents that match the query, re-rank the results based on the relevant score, and limit the number of records to be returned, and return the output as a list. Now here are the markdown files I will be using as my knowledge base. Each file contains rental property information, scraped from Zillow's website for either San Francisco or Portland. And finally, to set up the knowledge LanceDB database we will be using in this tutorial, create a function to run the setup. In the function, provide the database path, table name, and knowledge file directory path. Then call the create LanceDB table function to create the knowledge table, and upload the markdown knowledge files to the knowledge table. Now run the setup LanceDB function to perform the RAG database setup. And all 9 files are added. With the RAG knowledge database created, let's learn how to integrate a RAG database in PydanticAI. This part is going to be a lot easier since we have already done the hardest part, which is to set up the RAG database. Create a new Python file and let's name it agentrun.py. In the script, import the required Python dependencies. I'll be using 2 AI agents. One agent is going to look at the user's query and suggest a search query to search from the knowledge database. And the other agent is to be the user-facing agent to answer users' question. Create the functions to set up both the knowledge query agent and the main agent. I'm using GPT-4o mini model here for the main agent, but typically if you are working with unstructured text, research paper, documentations, scientific journals that are a bit more complex, you may want to use something more capable like GPT-4o or o1 models. In the main function, create an instance of LanceDB database object to connect to the database. Then use the openTable function to create a table reference to the knowledge table. Next, create both main agent and knowledge query agents. Now, depending on your use case, in some instances, you may not need to track message history for context. Like if you are running a one-off request, like retrieving customer's name or phone number. If that's the case, you can ignore creating the message history variable. To keep a conversation session alive, insert a while loop. In the loop, use the input function to accept user's request. We then pass the input string over to the knowledge query agent to suggest a query string to search the relevant information from the RAG database. From there, call the retrieve similar docs function with the table name and query string to retrieve the RAG content to be used as context. When we use any re-ranker class to rank the results, in the results set, it will add a field called relevant score to return the confidence score. Here, I'm only returning text content from the knowledge database with relevance score greater than 70% to ensure the context data is accurate and relevant. Depending on your use case, you may need to play around with the relevance score limit a bit. Concatenate the text string that meets the relevance score requirement and construct the prompt like what I'm showing here, with knowledge text as context, followed by the user query. And when we run the main agent, we will pass the modified prompt and print the output once we receive a response from the main agent. To keep message history as context, we need to update the message history variable in each agent run. All right, now we're ready to test the RAG database with our PydanticAI agents. Call the main function to start the conversation session. Okay, so here the LanceDB setup is executed when I import functions from the LanceDB setup module, which I don't want. All right, let's try again. For my initial query, I will ask, can you list apartments that allow pets? Based on the user's request, the knowledge query agent will look at the input string and suggest a knowledge query to be used to retrieve relevant information from the RAG database for reference. From the output, it returns 3 apartments, 1 in San Francisco and 2 in Portland. And if we ask a follow-up question to limit the listings in San Francisco, and the main agent returns the 4 rentals. I guess my system prompt is not detailed enough for the agent to use conversation history as context, but you get the idea. And that concludes this introduction to RAG agent tutorial. I hope you find the video useful. If there are any tutorial ideas you have in mind and you would like me to cover, please leave them in the comments below. Also, if you're a Patreon member, you can download the source code from the link in the description below. And don't forget to like the video and subscribe. Happy coding. See you in the next one.